So I was talking about this slide, and I think what most of us are used to talking about from the SCP perspective is these four. Usually we talk about four cases. We've got the baseline, and then base case, better case, and best case. And we put those on a spectrum as well in terms of how far down, how aggressively we're trying to reduce the energy usage of the building. And so we're here on this upper spectrum. I'd say we're focused on this left side in terms of the detail level. On the lower spectrum here, in terms of how far we're pushing these buildings, we talk about getting to the better case being usually about the life cycle cost effective, the lowest life cycle point. Base case, usually there's some more work that could be done to reduce those costs. And then up here, where many times it would take more money on an annual basis, or isn't fully cost effective at this point to push a lot of buildings all the way to net zero. That's something we commonly find, and that's not really a surprising result. If it was cost effective to push all buildings to net zero, and it was straightforward to do it, then it would be being done across the country. That would be common business practice. If all businesses want to get to the lowest cost point. So it's not surprising that that's either not feasible on the lowest cost perspective, or very complicated, so that not everyone can necessarily do it, even if it was possible, just because of the mix of complicated technologies or other things that are going on. And one other slide to add in. Here we go. So this is a common chart that we show as well that I guess just gives some depth in terms of the cost. Take a look at this. This would be kind of like an annualized cost, this total cash flow here. And we look at that being composed of your fuel costs and your kind of capital costs on an annual basis. And so here these are kind of points that we would look at that lined up with that lower spectrum before. So this might be the base case where we are right now. The better case being the lowest life cycle cost. This means that the combination of your capital costs and your fuel costs. Here, usually this is the fuel cost, and then this blue one is the capital cost. So they're calling it delta first cost, but the capital portion. And then your energy costs here. Where this is at the lowest point, that's often what we're looking for the best case or the better case. And then these would represent the best case, or that net zero position where there's a lot of capital cost. It can generally go up higher on an annualized basis than even your original, your base case. But there may be other reasons that you push your buildings to that point. So those are just some general overall ideas for the costing, and then we'll get into how this is done. All right, I've got a couple of his up here, just that it's that same one, but showing different areas. So taking a quick look at the tool, so Richard's looking primarily at the costs related to the facilities and those EEMs, and all of that's covered in that video. If we go forward to the installation or subsection, as a review, this is the area where we're looking at larger scale technologies. We assess PV here. We can look at wind turbines. More than anything, I would say we focus on central energy plants, heating, cooling plants, cogeneration at those plants, providing electricity. And this equipment and measures table shows all the technologies that we can consider that we already have models developed for. And when I call these models, these are the cost and energy usage models for these technologies, so that they can provide either heating energy or cooling energy or electricity for a group of buildings. We're here in previous sessions, we already laid out a group of centralized buildings that are all grouped together and decentralized buildings. So I didn't spend too much time when we went over this the last time talking about where these numbers come from. And we'll blow this up a little bit here. So each one of these rows, just as a review, is a technology of a given size that has some capacity associated with it, and then costs associated with that capacity. And the reason that we have a couple different sizes for each thing, so these are central plant boilers, large scale boilers providing either hot water or steam at a central plant, and we provide a couple different sizes so that we can capture economies of scale, and the cost generally goes down as you go on a per capacity basis as you go to larger system sizes. So we'll look at for example, these reciprocating engines. And here are the capital costs. Generally, there's a decrease per size of the cost, right? So for the 1 kilowatt unit, we should see that if you multiplied this by 5, it would actually be more than just purchasing this one that's 5 times the size. So that's the general concept. All of this information, all of these models, it took a lot of time to put this together, coming generally from either working with district folks and getting cost estimates or project costs for previous work at installations. Also from some of the larger scale engineering contractors that have put forth sometimes studies, sometimes just plans for the installations, other times bids to do this work. And trying to sum all those together, form some kind of distribution for each technology type, and then come up to averages basically, so that you've got some band there, some reasonable band of cost. Other things, generally the renewable technologies, those are published and then usually reassessed each year by NREL. They put out numbers on the costs. They usually give as well something like a distribution for the costs for different technologies, for solar, for biomass, for wind, a number of technologies that we can then integrate those numbers as well into our models. So that's where a lot of this comes from. And the nice thing here, as opposed to doing the facility costing, is that the equipment cost for a large scale piece of equipment doesn't change that much from place to place. You can have some differences with like an area cost factor, which we're working on adding in the ability to basically apply an area cost factor across an entire study, so it would raise the costs of all the installation costs, all the O&M costs, again just at a planning level. But if we can bring in those numbers, then you could apply it very quickly. But as opposed to the decentralized costs that we've talked about a little bit, if you're planning out boilers and chillers for 500 square feet or 5 million square feet of conditioned area for buildings, those numbers are going to be vastly different for the cost of that equipment. But here, if you have a known capacity, the cost associated with that equipment is relatively standard. Again, especially once you bring into account something like an area cost factor. So that makes it a little bit easier to do this kind of work, and we can use these tables of equipment models for lots of different studies. But there are some aspects that are more difficult. As I mentioned, the decentralized and also doing network costing, which I think has been known as a relatively complicated aspect to try to get good numbers on network costs. I'm talking about thermal networks for centralized systems. So we have a couple helper spreadsheets that I wanted to take a few minutes to go through. And we'll start with the decentralized costing one. So both of these are works in progress. And again, any questions, we can answer them here in real time. But we're developing these so that it will be very easy and quick to go through this process. We're mindful of the fact that once you go through all the facility work and get the EUIs out and all that, do the phasing, all of that work that's done, many times you're near the end of the amount of time that we have to work on the SCP in general. So we need this portion to go really smoothly, just so that it can be completed at all, I guess, is part of the concern. So if we go into the tool, let's go back here for a minute, over to facility loads, enter the password again, and go to the demand by end use report. Let this load up for a second. This actually, I wonder if this one hasn't been updated. I'm not sure what the issue is. Normally there's an Excel file download here in the demand by end use, and it may be just that That came out since the time that we started this study, so we may need to actually do an update to get it in the study. But there's an Excel download that you can get here that will show you the peaks broken down by each building type. So it'll show you the cooling peak, the heating peak, the electric peak, and let me show you what that looks like. So this is a download, and you can see the generic looking name up at the top. That was automatically generated by, by the tool, by the NZP tool, and the output looks like this. So this is the data it contains. The alternative name is listed here on the left, and then the facility type, the number of facilities in each one of the facility types, that total area, and then the peaks. And these are the peaks that we wanted to look at, and we're using these peaks to cost out the decentralized equipment. So the boilers and chillers that would be needed to meet these peaks, to do the cooling or the heating for the building, and similarly the domestic hot water. So there are potentially 5 categories. We've got cooling that's done electrically, gas heating. It could be, like a boiler system. Gas source for domestic hot water. These two, again, would be the most common. And then there are some situations, especially for remote facilities, where we may have some electric heating or electric hot water systems as well to do the domestic hot water heating. With this group, with our current study, we don't have any of those, and this is going to be the most common situation anyway. But we have the peaks here, and they can be broken down on a per building basis, and so that's basically what this spreadsheet does. There's a lot of calculations that go across, and this has to be done, it has to be generalized in this spreadsheet so that we can have as many alternatives as come out of the tool, which could be, commonly we usually only have something like 5 or 6, but we could have many more, so the spreadsheet could be used even when we have a high number. This is, I mentioned the output of that report, but I'm providing this template back, this spreadsheet template back to the ITL folks that are going to then integrate it so that they'll dump the data in here and we'll still get all the results back out. So there's a lot of work that goes on in this spreadsheet, but the only thing you'll have to look at are those total costs. So the total cost here in this final tab, and that's going to give you the costs for each scenario going across. Here in our study we only have 2, but each one of these will fill out as data is available, and you'll get the cost for chillers, the cost for boilers, the cost for the natural gas domestic hot water heaters, and you can use those numbers and input them directly into the tool. So it's not a thing that's done in an automated way, entirely automated at this point, but the same way that we went through before during this section as we were going through and setting up the baseline and base case, and we had to calculate the costs for decentralized equipment. Here we can just download that spreadsheet and all the work will already be done. We'll just zip over to that tab and then enter those numbers here in the installation costs. So that's, again, just to speed up this process, to make it really easy and reduce the workload. Any questions on the spreadsheet or where any of that comes from? There's a little bit of background information. Again, we're continuing to clean this up. All the costing information comes directly out of RSMeans, and the tables are provided here. So you can see the peak numbers. Anyone who's done this kind of work before to cost out equipment for a single building, which is a pretty common task, would likely be familiar with some of this kind of work. The text this comes from, there's escalation rates on all of these. We can get, at any point we'd be able to replace these data sets. That's the idea, that we can update this over time. This is a good starting place, and then these can be updated, and it will make it very easy to continue going forward and using this. And we'll be able to provide, a new spreadsheet. Another benefit for doing the work this way is that it's very transparent. I think a lot of people are very familiar with using Excel, and so if they have any question, they can come in here. Assumptions should be listed out, and you can make any changes and ask any questions, and we can make updates going forward. You can usually get RSMeans data, so they come out in usually giant textbooks of data where they itemized through all sorts of costs related to lots of different industries, but primarily the work that we're interested in has to do with buildings. So there's costing information for plumbing systems, for all the HVAC that we're interested in here, foundation work. All that kind of information is present in RS Means book. So it's basically the company that produces this is like a cost engineering company that are now well established and familiar in in the group of people that do this kind of work, that do costing work. And so they do break it down as well by these system types. By what we're looking at here are generation systems. So it's not the building distribution, where you might talk about different types of building distribution systems, like radiator systems or fan coil systems or something like that. That's all within the building after you get your heating or cooling source to the building. And what we're talking about here are specifically the generation systems. So the boiler itself that's going to have some connection with either a heat exchanger or going directly to those, like a fan coil system. It's those systems where you could change that out directly with a district heating system that has a heat exchanger. So if we can kind of get right up to that point of the heating coil or the cooling coil on an air handler, those are the systems that we want to be able to compare against each other. Does it make sense to have our generation come from a central plant, or does it make sense to have these boilers or domestic hot water heaters right in the buildings? And so that's where we're looking at the differences, and we've got to separate those costs out, and that's what we can find in these RS Means documents. And I tried to give even the title of the text that was used, the page number, all the information down, so that it could give a little greater confidence when people are going through this, and also so they'd be able to make changes going forward. If you get a new cost table, you can see this is actually fairly old data. It's 5 years old. Hopefully we'll get a new text in shortly and update it, and we won't have to use an annual inflation rate to multiply this up. We've got base numbers here from that year, and then those are inflated up to 2016 numbers. So, and all of this is being done, we're talking about it being done at the planning level. These don't need to be exact numbers. There's a fair amount of, of an error bar, but at the same time, I had a conversation with Susan not long ago about this. When you look over the course of 25 or 30 years, the cost, the absolute installation cost, and along with any financing costs and things like that of the equipment, is a fairly small portion of the total costs of providing heating and cooling to those buildings. It might be something on the order of 25%. So knowing that, if you're plus or minus even 20% on that number, and let's say it's 25% of the cost over a 30-year period, now you're looking at a very small portion. You're looking at 20% of 5% of that 25%. So 25% plus or minus 5% of that 30-year cost, which is a smaller fraction. I think it helps put into perspective that even a small error here is an even smaller error when you're looking out over 30 years, and a large portion of that total cost has to do with the fuel and the efficiency of the equipment, and any synergies involved there. The investment costs are listed here, but we also get estimations for the operations and maintenance costs. And those are listed as, this is a relatively straightforward aspect for doing these calculations. They're listed just as a percentage of the investment cost. And we've got a couple notes here. This is, again, a method I'm hoping that we can continue to provide, where we give kind of a default value and then some notes on what numbers would be acceptable. I'm hoping that we can work with Richard even on some of those, on the facility numbers. There's a giant table of parameters related to the facilities, and just talk about what's an acceptable range and what does each one refer to. Things like with the windows, what is a triple pane window? What is an appropriate U value for that, and what's the U value for a single pane? And it gives you a range so that you can say, all right, I know what these are. These windows look very much like they're single pane, and so I know that it should be close to this value. Trying to provide helpful ranges like that, I think, is going to also continue to provide value here. So I've given a 5.5% of the annual, or an annualized O&M cost of 5% of the installation cost, which is a pretty good estimate. And here are the range numbers. If we had brand new equipment, say this is these are all going to be built in this next period of time. None of it's not existing equipment. We usually go with something like a 4%. That's just going to be periodic maintenance. Most of the stuff's in good condition. There's not a lot of significant issue. If it's older equipment with frequent servicing, about 7% of the annualized cost of putting new equipment in is about what you would expect for O&M costs. If we get to the point where we're actually replacing some of the equipment on an annual basis, so some of it is failing and we're including the annual cost of installing brand new equipment, then we get to something like a 10% of where we're frequently switching out that old equipment, and that capital cost is included in this O&M cost. So it just gives a range, and these numbers as well would go directly into that table of equipment and measures. But it'll automatically be generated. There won't be anything else you'll have to do, just understanding where it came from and being able to explain those numbers. Okay, so the next one, there's only two here. I realize that there's a lot going on, but it's going to be very simple to use. So it's just the explanation of how it works, because when you actually use it, you'll just download the spreadsheet and all of these numbers will be populated. So the next biggest difficulty on the installation side is trying to determine basically the parameters related to a network. So the cost of a network, the storage potential for the network, those kind of numbers. So if we go back over to this is how I would usually do the costing. We'll look at the centralized buildings here. We'll open up the map. We'll say these are the centralized buildings. Again, we're working on features, hopefully for the future, where we'll be able to actually draw on lines and have it show you the distance for those. That would be a helpful feature here. But we do have a scale on this lower left, and normally I would find the central plant, or the position of the potential central plant, and then map out the approximate distance around buildings so that I could get a pipeline network to those buildings. Now here, a lot of times we've got a plant and then a set of buildings that are a little further away. So, because either the exhaust stack goes up fairly high and they don't want it to be co-located in the middle of a group of buildings or something like that, that's often what happens. Here we're kind of right in the middle, but if we wanted to figure out what the load would be and what size pipe we would need, the first thing I'm going to do, this is all temporary, I'm not going to save it, so I'll remove these from the selection. And you see they're not that teal color anymore. And now I'm going to say just add these lower buildings. We'll say just go with this group here and calculate the load information. And it's going to give me a heating peak. So if I pretend like this is the central plant, here we didn't actually designate a single building as the central plant for these buildings. I may be having some kind of connection issue. We might have to go back out of this. Here we can see the space heating peak for the entire group of buildings is this 33,000 kilowatt. So let's say it was about 10,000 kilowatt. We can go back over to the network tool, which was the next one we're going to take a look at. And what did we say that was going to be, about 10,000? If we put that peak in here, it will calculate a pipe size. So you don't really have to adjust anything else. It's default values in here, and you can calculate what the size of the main leaving the plant would be. So you get a value in there for this. So this is going to say it needs to be at least 11 inches, if you're going to go up from there, to meet the minimum flow requirements. And the next tab, you can do, you can cost out the network. So if we went back over here, looking at the network, and say we determined the size for the whole thing and we knew what pipeline sizes we were going to need, we can just sum up all of those. So we've got a pipeline going out over here. Commonly, you'd actually have a loop, something like this, that comes back around if it's in this kind of a configuration. If you're further out with a building like this, you might have a single main coming here, and then you would break down to smaller pipe sizes as you go out to further extend out further from your main network. And you would come back and add up those portions. So you might say that we've got a 12-inch main here that's going to be 3,000 meters long. We need to have twice as much pipe as that because it's a two-pipe system. There's one going and one coming back. And then we might have other sections coming off where we've got like 5-inch pipe, and we've got 2,000 feet of that, and then some 4-inch pipe as well. And all of these you would be measuring out and calculating the distance and measuring or just summing up those sections, as I was showing that should have been working there. Again, there may be some issue because I'm sharing and we've got a web meeting and a bunch of other things going on. I've never had it give me trouble in the past with doing this. Let's try one more time. So you can see all the information over there. Looks like it's going to work this time. All right, so if you click calculate, you can get those loads. So there's the space heating load of 20,000 kilowatt. Again, you just drop that in as the uppermost number on that far left side. Looking over here. And you can get the size requirement for that main. So you'd add them up, put them in through here, and we can actually find the total network cost. This is going to sum up the pipe costs that are going to show up here, and then construction related costs. And again, these are works in progress, but we're trying to provide the itemized cost for each one of these as well, breaking it all the way down. So we've got the pipe cost and the network cost here. You're going to get a total cost for your whole system. That's all that you would need in terms of the costing to put into the tool. But if you want to be able to provide more detail, you can actually go down to this lower section, and we're trying to break out all of those costs. So these are all costs related to the pipe itself, pipe size, elbows, reducers, anchors, all of those things that are probably unfamiliar to most people, but at least you can show that breakdown. So if you've got a facilities engineer, they're in the room and they say, yeah, I don't know where this number comes from. It's just coming out of nowhere. You could say, look, all of this is broken down. That you could have a discussion on where this information comes from. And then similarly, you could kind of look at this as having two main components. This cost for the network, there's a component related to the pipe itself, installing it and all the components, but then also a portion related to the construction, to how is it placed? Is it put in overhead carriers? Is it in utilidors? Is it direct buried? All of those costs as well are shown down here below. So these are the construction costs here. And then all those, you'll see that 63,000 number is going to be the same number that we'd see right here with the construction cost. So it's just broken down, itemized throughout. The only numbers you're going to need are going to show up here. There's a little bit more work doing this network calculation, but still so much less work than if you had to try to do something like this on your own. I think there are like 4 or 6 more hidden sheets of calculations that do all of this behind the scenes and bring it all forward to these itemized lists here. Basically look up tables and references and things like that. And then another small tab over here just to calculate the storage. So looking back over to the NZP tool, remembering all of this was to try to cost out those two components that are relatively difficult to do. They can't really be standardized. They're not standard costs for a set piece of equipment. They've got to be related to the equipment that you have, the space. The network's going to be related to the amount of space, how much length, how complicated is it to do the actual network itself. So that's why we've got these two helper spreadsheets to do that work. And that network, again, as a reminder, is going to be entered in here. So if you can put in this thermal distribution system, and you can do it for either a hot water network or a chilled water network. So you could do that either way. If you're going to do both, if you're having, say you're doing planning for a new district, and it's right now it's just a field, and they want to know the difference. They want to know whether or not they should centralize it or decentralize. This was actually a project, a planning project that I just presented on this past week, was asking that exact question. They were located relatively close to an existing central plant, and they wanted to know if they should just decentralize everything, if they should have their own central plant, if they should be connected to the existing plant, what technology should they use. There's a lot that would go into this, and it has big long-term implications on the energy use for that group of buildings and the cost. And the solution that we found ended up using about 60% of the energy on an annualized basis. I think maybe even a little bit less than the decentralized solution. And you could get there because they had an existing central plant. You could get there for an even lower cost than having that decentralized equipment. So it was both lower cost and lower energy usage. And again, those are big decisions to be able to make for groups of buildings that may be nearing 1 million square feet in conditioned area. But those are the kind of things that the tool helps you to do, and these spreadsheets would be a big part of that. So I realize this is going to be unfamiliar. Going back to this spreadsheet for a minute, there are different construction methods here, and so you'd have to break it down. Most installations choose to do direct bury, where they just, as it sounds, they would directly bury the pipe in the ground right there. But you've also got these other options that again are itemized out below, and these are going to be you just write them up as fractions. At this planning level, you'd say, if it's 80%, you could just put 0.8 in here, and then 0.2 someplace else. You're just going to be dividing this up as fractions. And then similarly, the difficulty of laying this network, and this would have a light, medium, or heavy, and there are notes on what does this mean. So heavy would usually say, if it's a very rocky terrain, or if they're already a highly developed area. So, for example, Minneapolis-St. Paul has a huge thermal network. They've got a great system set up with cogeneration of heat and power. But any new network line that they put in, they basically have to dig up sidewalk or something like that. It's very difficult. It's very expensive to do that. So the upside for them is that they've got a huge heating need and dense power needs or dense heating needs as well. So there's big buildings that are close together. They don't have to go very far, and it's very cold. But the downside is that they've got to go through existing paved areas, and so we would say generally that's heavy difficulty, and then just generally lays this out for planning purposes. You can see if I change that over to heavy, it makes a huge difference in the construction cost. And this went up by over a factor of 10. But the piping cost stays the same. So just some of the aspects here, looking at it changes and what you might plan for. You may have something that's in between, and you may be able to say, well, part of it is very difficult, and part of it is going to be like a green field, like a field that would be very easy to lay this piping in. And so you could break it up in some way that way as well. But just a really nice resource that you wouldn't often have access to unless you're working with an engineering firm that does this kind of work regularly.